All right, so how do we going to do it? Let's start here. I'm using std dev for standard deviation, so just mind you that. All right, let's look at the mean. Mean mu. Now, if we look at the table we created last class, we are seeing similarities between that probability distribution and a frequency distribution. Yes? We had some value, right, or class, and we had some frequency. In this case, we have value and probability of that value happening. And so how did we calculate mean in a frequency distribution? High statistics. It's stuck on itself. Cannot forget.
All the values divided by the number of them?
All the values is not bad. A start, that's an average. That is slightly different. We did sum of x times f over n. Right? We did the frequency times the value, sum those things up, and divide by n. Yes? Maybe? Possibly. Okay. Well, we can rewrite this as the sum of x times f divided by n. And the reason why we can do that is, a short example is 1 plus 3 divided by 2, or 1 divided by 2 plus 3 divided by 2. Those two things are equivalent. Right, so this is what we are doing. I'm dividing each one of those things individually. Right, so that's simple. Now, you okay?
Yeah.
Okay. If we look at a very simple example, what's the frequency of x's? Right, frequency of x's is 2. What's the population size? So what's the probability I'm going to pick an x at random? Yes? So in our case, this changes to the sum of x times probability of x. Looks familiar?
No.
Looks terrifying.
Terrifying.
How can I help?
Oh no, it's fine. It's just
Think about it this way, right? If you ever get stuck with probability distribution, think about a very simple example, right? Same with this. Think about very simple examples. Okay, and there's the mean. Done and done. The mean is the sum of x times probability of x. What's another term for mean? When you talk about means, what else can we say? Average. What else? Center, right? Middle or center. And one last one. Sorry? No. Midpoint has a very specific meaning, but middle is close enough. I would say, how about the expected value?
What did you say?
Expected value. Right? If the mean height of a pizza delivery or mean age of a pizza delivery guy is 20 years of age, if you open the door and there's somebody between 17 and 23, are you surprised?
No.
Somebody shows up at 67, you're going to be like, whoa, dude, you know? Kind of sketchy. Or if a 5-year-old kid shows up with your pizza. Sir, Can I get a tip now, right? That becomes, so we can also look at the mean as the expected value. Right? If it is the middle of the pack, then we are going to expect the middle of the pack. Right? If the salary for your job is on average $50,000 a year, if you're applying for the job, what are you expecting to get? About 50, right? Maybe 45, maybe 55, maybe some perks, but 50,000. Right? So this is also called the expected value. So when we talk about means, we also talk about expected values. All right. We had this table last time of a very lucky die, which had 6 sides. And slightly adjusted probabilities. What you would, 15. What you expect from a regular die. Remember that one? All right. I'm going to keep on working on this table, and this table is going to have at least a couple more columns. So if you're writing it at the edge of your notebook, you might end up being surprised. So we had this table. So let's look at this table. What is the expected roll on this out of this die? No. Well, I'm going to get 1 out of 6. What I'm expecting? No, this is the chances of getting a side. I'm going to get a side, right? But if I roll this die, what would you expect to roll? 3 or 4, right? Right, that's expected. So if I roll this die enough times, the average of those rolls is going to be, well, it's going to be this. Right? All right, so how do we calculate it? I'm going to put an extra column here. X times P, right? Again, I'm following this formula, and just like the Shrek, I'm peeling it from the inside out. Sorry, as an onion, Shrek. As the onion, I'm going to peel it inside. All right, so let's multiply it out. 0.05, 2 times this, 0.30, 1.05, 1.20, 0.50 and 0.30. And if you guys would like to know that, I is putting dots instead of commas.
What's the probability of 4 greater than 3?
That's not the probability. That's the value of this times the probability. 4 times 0.3 versus 3 times 3.35, right? This is just a mathematical outcome, right? Just like we did before, we did frequency times a value, right? 1 8-year-old guy could beat 3 20-year-old guys when it comes to age times frequency. All right, so we got this. This is a 0, sorry. 0. Okay, well, last part, the sum of the whole thing. So I'm going to sum the whole thing up. Sum of x times p of x. And I'm going to come out with 3.4. And here's the question number 1. Does 3.4 make sense as the expected value? Why not?
Because you can't get a 0.4 on a die.
True, true. But you cannot do a lot of things. Question is, doesn't make sense.
Yeah.
Right? So here's the question. This is an average, right? So if I roll a die once, 3.4 doesn't make sense.
That's about your line between.
But if I roll a die 1,000 times and I average those rolls, right, 3.4 is actually making sense. Here I would expect to get a 3 or a 4, right, because those are the highest probabilities. So 3.4 makes sense, somewhere between 3 and 4, right? If I roll 1,000 times and average those 1,000 rolls, I'm going to get this. I'm expecting to get this. Now, even though I'm expecting this, can I still roll a 6? Yes. There's still a chance to roll a 6 or a 1. Right? So this is not guaranteeing a 3 or a 4. This is just saying, hey, if I roll this die, I'm going to expect to be about 3 and 4. Can I get a 1? Yes, I can get a 6 as well. And I'm going to be expecting it to roll here. On a single row, and over a long number of rows, I'm going to expect it to, the average of those rows to come out to 3.4. Good. All right. Moving this aside. Let's look at variance. If you look at variance, well, what's the symbol for variance?
S squared?
Yes, but that's for sample. What are we dealing with? Of a population, right? X bar is for a sample. So we're talking about a population. So sigma squared or Cannon squared equals to sum of x squared times p of x minus mu squared. Now, big and scary? Yes. Can we do it easily? Yes. But before we start playing with this, let's go and do standard deviation while we're at it. What's the formula for standard deviation? What's the symbol for standard deviation?
Same O,
Sigma.
sigma. That underscore root. So you just move it over, yeah? You square root the whole thing.
Yep. That's it. The difference between variance and standard deviations is the square root. Mathematically, right? I just take a square root of this, or I take a square root of this. All right, so we have those two formulas. Let's go back to our table. Now everybody has their method of dealing with variance. The way I like to do it, or the way I would recommend do it, is let's do x squared first, because that's usually going to be a very quick calculation. Right. X squared. Let's start with x squared first. So what's x squared? 1 squared 1, 2 squared 4, 3 squared 9, 4 squared 16, 5 squared 25, and 6 squared 36. I'm just squaring the thing on the very beginning. Again, you just look at the top of the table and you know exactly what you should do with all the previous things. The second part of the second column is going to be x squared times p of x. So x squared times p of x. And how do we get that? You take x squared times p of x. Those two. Everything that you missed is on the board already. So, 1, 2, 3. Is everybody comfortable with filling out a table like this? So far, so good? Good. All right. So, last step. Oh, on to the last step. Sum of this. Sum of x squared times p of x. Sum of x squared times p of x is sum of this column. And that sum of x squared p of x comes out to be 12.9. I just added those things up. Again, if you have a calculator, that should be relatively easy to do. All right, I see some blank stares. How many of you are getting a little overwhelmed by the numbers? You don't have to raise your hand. Is there, right? How to do those type of problems when we're talking about probability distributions and we're talking frequency distributions is you have those formulas. You're going to have those. You're going to put them in your little cheat sheet and you're going to be golden. And then you just start pulling things from the beginning. What do I need? I need an x squared and I need a p of x. I have an x, so I'm going to make a column of x squared, and I have a column of p of x, so I'm going to multiply it out, and I'm going to add. You do it systematically. Lots of numbers, yes, but I've seen people balance their checkbook. This isn't much more difficult. Systematic, one step at a time. You start with 12 values, just expanding them. Okay, so what's the variance? Well, we know that the variance is the sum 12.9 minus mu squared. What's mu squared?
Mean square.
How much is the mean?
Further down, super.
Sorry? How much is the mean?
3.4.
Yes. It's right here. So minus 3.4 squared. 3.4 squared is about 11.56. So that comes out to be 1.34. That's the mean. If I square it, I get 11.56. 12.9 minus 11.56, I get 1.34. And how much is the standard deviation? Well, the standard deviation is sigma equals to square root of 1.34. That comes out to be 1.18. 1.16, sorry. 6. As far as difficulty of calculations for this little section of statistics, this is it. This is as difficult as it gets. Is picking the right formula, frequency distribution versus probability distribution, and then building a chart where you can just multiply things out. This is the difficult part. This is it. Mathematically, this is it for this little section. There's no more. Let's go home. No. No. We have more. Will you be able to see it if I shift it over? All right.
How are we going to get on the quiz that requires the variance to do all this stuff?
Okay. How
I
about?
understand the math at this point, but we need to understand the question.
Okay.
Just give us like a chart.
No. What I'm going to give you is, if I'm going to give you something like this, I'm probably going to give you this part
Right.
and ask you about what's the mean of, I don't know, this dice roll, right? What's the mean or expected value of this dice roll? Or I could give you an example like this. Example, Do I have it here? No, but example. Let's look at the loaded die. What rolls would be unusual?
1, 2, 6.
I see 1, 6, 2, 5. I mean,
What's the lowest probability would be 1 and 6?
A loaded die means loaded on any number.
no, this loaded die, this specific loaded die.
Yeah, 1 and 6 are the lowest.
They're the lowest. What happens if one of them is 1 and the other is 5? Right? Right now you're just picking the lowest, and they are very different from this, right? 7-fold difference, but that's not a good enough answer. I want a reason, right? You're talking about decision making. Let's make a decision, right? If you're talking about parts failing, chances of parts failing, or succeeding manufacturing something, right? This is a very reasonable table. So the question is, what's unusual?
1.
1 is unusual. You said about this. That's it?
Yeah, because 1 is more than 1 away by standard deviation. Or what?
All right, so how do we define unusual? Let's go back to the basics. How do we define unusual?
Do you consider an outlier?
No. Outliers are different. What's unusual?
Anything that is like either too high or too low.
Yeah, to what? Too high, too low what? To standard deviations, right? So what we are looking at, saying, hey, if we have a mean here in the middle, and we have mean plus 2 standard deviations here, and mean minus 2 standard deviations here, everything outside of that is unusual. This is the usual range. Yes? Okay. Now, I'll help you. Mean is 3.4. So how much is mean plus 2 standard deviations? How big is standard deviation? Standard deviation is 1.16. Yes? So what we are looking here is 3.4 plus 2 times 1.16. 572. Right? So that point is 572. How about the other way? Well, again, this is 3.4 minus 2 times 1.16, and that comes out to be 1.8. So what our friend in the back is telling us, everything bigger than 5.72 or smaller than 1.08 would be considered unusual. So what's bigger than 5.72? Well, 6 is bigger. 6 is bigger than 5.72, right? 6 is over here. There's 6. 6.0. Is 6 bigger than 5.72? Okay. What's smaller than 1.08? 1 is smaller. Why? Because 1 is right here. Yes? So, if I look at this way, okay, unusual means outside of 2 standard deviations. So unusual is 1 and 6 are unusual rolls. If I get this die and I start rolling a lot of 1s and a lot of 6s, I'm going to be like, well, this die is not behaving the way it's supposed to. It's unusual to roll this many of those. Okay? Now again, this is easy because it's a table of 6 with a bunch of probabilities, right? But this can very easily become very, very big, right? If you look at, what was the last statistics I saw? Humvees. They were doing plating underneath the Humvees for Iraq and Afghanistan. And I was looking at at some data. Some of my students who were in the military brought their testing data. And I'm looking at the failure rates. And they're like, well, I was asked to figure out what's unusual. And those numbers go up very quickly, and there's a lot of them. And you just have to, plug it into Excel. But question is what formula you're going to use and how you're going to approach it. Unusual means 2 standard deviations. Okay. Easy. So far, so far. Empirical rule. Who remembers empirical rule? What?
I can look for it.
You can look for it here. Not good enough. What did empirical rule say? Within 1 standard deviation, 68% of the data is within 1 standard deviation, right? 95% of the data was within 2, and 99.7 was within 3. So, if that was the mean plus 2. That was the mean minus 2. Yes, 95% data was within 2 standard deviations. How much data is outside of those 2 standard deviations? 5%. 5%. You don't say. We consider probability of 5 or lower, 5 or less, 5 or less, 5 or lower, 5 or less, 5% or less to be unusual. So I'm going to put it over here. %. What's 5%? Right, 0.05. A is considered unusual. Okay. Can I take the table out? All right. So let's look at something a bit more extreme. What happens if we flip a coin 1,000 times? I promise not to make you make the sample space for that, because that will be cruel and unusual. And I'm looking for probability of exactly 501 tails. What is the probability? If you had to take a wild guess.
50.0001 or something.
Oh, really? 1 or 2. So you have 2 sides.
Well, what's the probability of getting 501 tails? I hear 50%, about.
1%.
Sorry?
50.1.
50.1. Can I hear higher?
51.
51. Okay. And here comes the reality. It's 2.5%, a little over 2.5%.
Exactly 501 tails out of. Oh, okay.
Okay, let's look at something different. Probability of, what's that? Oh, 501 or more tails. What's the probability of 501 or more?
Oh, or more. Then it's like 50 grams.
50
Or more. Is it 49?
Close. I see your faces, and I'm going to do it again. Mind blown.
Gotta figure out why.
No,
Yeah.
I mean, we're just doing math wrong. Because for that 501 is just one time, yeah? One time of getting that out of 1,000, but then the 501 is 501 to 1,000, right? That's why it's high.
So the next section we're going to deal with is binomial distributions, binomial probability distributions. And until this concept of those two numbers sinks in, we're going to have a lot of struggle. And the farther we go in statistics, the bigger problem is going to be. If you can wrap your head around those two, then the rest of this chapter and parts of the next chapter are going to get very easy by comparison. So let's look at it. You're flipping a coin 1,000 times. What are you expecting on average?
You pick 52?
You're expecting 500 heads, 500 tails. Easy. Yes, everybody's with me. What are the chances I'm going to get exactly 501 heads?
1 in 1,000.
No, 2.5%. Right? But what I'm looking for is one very specific outcome. Right? If you start flipping heads at the very beginning, you're like, hell yeah, I need more heads, or I need a lot of tails, but I don't care. Like, I'm going to get the heads out of the way now, and I'm going to start getting heads, and start get tails, and then I'm going to get more heads and more tails, and eventually you're going to get to, 500 tails with 200 flips to go, and you're like, well, I just need one tail, and you're screwed, right? The amount of choices to do this is a lot, and you want only one of those outcomes. Right? That's why it's so low. Okay? Now, on the other hand, this one, 501 or more. What are the chances you're going to get 1,000 tails if you flip a coin 1,000 times? Oh, you wouldn't bet your house on it, would you? Probably not. It's slim to none. In scientific terms, it's slim, very slim to none. Right? Okay, how about 99 tails out of 1,000 flips?
Ooh, that's slim to none too.
Is it better than it was before?
Yes.
I would take those chances, right?
Yeah,
How about 998?
No.
It's still better, right? It's better than the last one.
Yeah.
Right? But no. The idea behind the difference between this and this is that here all of those flips at close to 1,000 have very close to zero probability, but the probability is nonetheless, and then adds up, right? Because you're adding all the probabilities of 501, 502, 503, 504, 505, 999, and 1,000, right? So after you add all of those up, even though each one of them is very, very small and goes to slim to none, that comes out to be 48, right? Any of you had a cockroach in your kitchen once? Right? One cockroach. I get cockroaches once every 3 weeks. I get a cockroach in my kitchen. One. I don't get a lot. I get one. Right? The chances of a cockroach being in my kitchen when I wake up in the morning, slim to none. Right? But if you compress all the days together, all those probabilities, it happening at least once a month is very high. Happening on a specific day is slim to none. Right? It's one grain added to one grain to add to one grain added to one grain. All right. So with that mentality, let's look at binomial distribution. Binomial probability distribution. And binomial probability distribution What does binomial mean? 2. Excellent. So binomial probability distribution has this one really awesome feature. It is a probability distribution that has only 2 outcomes. And we call those outcomes success and failure. Now the common misconception is that 2 outcomes are good for coins and that's about it. But there's a lot of things we can push under a binomial distribution. Gender. Oh, 2 outcomes. Easy. Okay. How about passing a test? There's 2 outcomes, right? Rain, sunshine, right? War, no war. Electricity above certain level or below certain. Battery charged, not charged, right? There's a lot of things that we can nitpick to a lot of different options, or we can simplify to 2 choices, yes or no, right? So binomial distribution is relatively powerful as a tool. And so it has several rules we should probably cover. It has the following rules. So, rules. 1, because we are dealing with a very specific success and failure outcomes, we need a specific number of tests or polls we go around. And so must be a fixed number of trials. It must be fixed. So if you have something that you cannot fix and close, you cannot run binomial distributions. 2, trials must be independent. Fixed number of trials, what does it mean to be independent?
Not affect others.
Exactly. The outcome of one trial does not affect others. 3. 3 is relatively obvious. There's only 2 outcomes. How would you like a coin that flipped more heads the longer you tossed it? That would be a fun coin to have, right? After the age of 7, that coin tosses only heads, right? So for binomial distribution to make sense, the probability of success remains the probability of success remains the same in all trials. And that's important. Can somebody give me an example of how we would get this done? Fixed number of trials. I'm going to send a poll to 1,000 people. Trials must be independent. Hopefully they don't talk to each other. Each trial has two outcomes, success and failure. Yes, ask them a yes or no question. And probability remains the same in all trials. Well, people are peoples. It's not like we send it one to the monkeys, right, or to the zoo, or to kids, right? We send it to adults. So all the adults, assuming, are going to answer with the same probability of something, right? This is how it's done. So if you're looking polling data, this is how it's done. It's based on probability like this. Okay. Well, we should probably enter some notation, just so we can do it. And the notation we have is N. What was N standing for?
Number of trials.
Yes. Okay, then we have a small p. Big P was what?
Population.
Big P was probability, right? So small p is still probability, just small p refers to the probability of successful outcome in a single trial. Then we have Q. I know the younger part of my audience will understand QQ. No, apparently. No, QQ as in crying. The emoji QQ. You guys are used to the actual printed picture emojis. What happened to ASCII emojis? I'm so old. Yeah,
It makes.
yeah, crying. Two eyes that are crying. QQ.
Yeah, I don't see it.
You haven't been on fortune yet, apparently. All right. This says what? The probability of what? Well, if we are talking about only successes and failures, and we just talked about successes, then Q is the probability of failure. So much fail or failure. It's so hard to have popular references when the age group is spread out between what, 20 and I suppose you guys are like what, 32, 33 maybe? So difficult. All right, then we have X. X is defined as the number of successful, number of successes that occurred or that occur in the N trials. And then P of X, the probability. Right. So N is the number of trials repeated. P is the probability of successful outcome in a single trial. Q is the probability of failing outcome in a single trial. X is the number of successes that occurred in N trials. And P of X is the probability of getting X successes. Now here is a public announcement number one. Public announcement number one is P, X, and P of X get mistaken between themselves. It's very common for me to find a homework or an exam that has those things mixed up. So just, at least for the initial time being, be very, very careful not to mix P X, and P of X. P is the probability of success in a single trial. X is the number of successes we're going to get in those n trials, and P of X is the probability of getting X number of successes. They're all connected, they're all talking about a very similar things, they are different. So just be very, very careful. All right, let's look at the first one here. Flip a coin 1,000 times. I don't get to be lazy very often on the board, so I'm good. If you flip a coin 1,000 times and we say probability of exactly 501 tails is 2.5%, what would be N, P, Q, X, and P of X? N is 1,000.
It's 499. Oh, would tails be considered odd?
And here we get. Excellent that you guys went after it, just trying to plug numbers.
P would
A
be
very easy way to deal with this problem is to do the following. Answer this question. What's considered a success?
Getting exactly 500
No.
tails.
Right? What's a success? You want a single trial.
Also,
You flip a coin, right? We flip a coin 1,000 times, so there's 1,000 trials. One trial, what's a success? A tail, for example, right? You could say a head, but a tail. So a tail would be a success, right? We want more tails than heads, so we would be happy to get more tails than heads. So probability of success in a single trial. What's a trial?
one,
No. What's a trial in this case?
one flip.
One flip. And if success is a tail,
one or two.
one of the chances, 50%. Okay.
So Q would be 50%.
Okay. Which brings us to a very cute thing, is that since we have only two outcomes, they have to come up to be one, right? Which means that we can arrange, if you only have two outcomes, the probability of either one or the other. You have two-sided coin and one side is weighted, you're still having only two sides. Tails and heads, right? Yes and no. Don't you love when you ask somebody a yes and no question and they go maybe? Right?
Third option.
Sorry? Yeah, there's a third option. Are you a United States citizen? Maybe. Are you working for ICE, right? Question for question. So if we have only two outcomes, probability of one tells you what the probability of the other one is, because together they have to be one. And then you can move them around. All right, so what's X? Well, X is defined as the number of successes that occurred in n number of trials. 501. And what's the probability we're going to get that number of successes? Being able to do this relatively reliably covers almost every problem in binomial distribution. Because what you're going to get is something like this, and what I'm going to ask you is to do something with those numbers afterwards. As you cannot go from here to here, from English to math, or back from math to English. Talk to me. Anyway. Don't look at me like I'm a crazy person. I actually like statistics. I'm like the only one in this classroom that likes statistics.
Watch it after I pass it.
No, you will forget it after you pass it.
I don't like it.
I still like it. I took statistics. There's like a B plus thing in my upping my GPA. I'm happy with it. All right. All right. Let's look at the example again of the loaded die. The loaded die. If you remember the table, the probability of rolling a 4 was what?
35%.
4?
No, 30.
It was 30%. Okay. So the die is rolled. I'm going to need a lot of board. Yeah, I'm going to move this. How do I do it? Can I raise this?
Yeah.
I'm going to need a lot of board just so I can move things around. Let me just go this example. No, unfortunately, I wrote on the back. It's 30%. The die is rolled 10 times. Find the probability of rolling exactly 8 fours. Can I erase this part? Oh, this is starting to be fun. Rolling once, we all can do it, right? That's level statistics. Now here it becomes fun because we are starting to get to bigger sets. If we can start being bigger, more complex sets, we can start adjusting them more. All right, well, let's start with the basics. N, P, Q, X, and then what's a success? And then how about this side? Because this side has been very quiet. Pick one and let's see the answer. What's a success? Hi. All right. What's N, what's P, what's Q, what's X, and how would you define a success?
Success would be rolling a 4.
Yeah. That makes sense. Okay. So success is rolling a 4. How many trials are we going to run? 10. What's the probability of a single success?
30.
30%. And I'm not going to do 30%. I'm going to go 0.3. What's the probability of failing outcome? 0.7, right? Because they together has to be 1. What's X? How do you define X? X we defined as the number of successes we want to get in n trials. And we want to get 8. That was an 8. All right. All right, here comes the big math part of this. So what are we looking for is P of 8. All right. On this side of the board, I'm going to solve it numerically. On this side of the board, I'm going to produce the formula. So I'm going to use 2 of those just to expand it. It's not very tall, but so binomial.
So are we looking at every time that the probability that you over succeed on your rolling a 4, it diminishes on your chances, right? So,
No,
so out of 10, 30%, so 3 out of 10 times you're gonna get a 4. But if
you're
you
expecting.
Yeah, you're expecting that, but if you expecting 8 out of 10, then that percentage diminishes by.
I'm not expecting. I want to know how was the probability of getting it is. Expecting means a mean, right? When you start talking about expecting, right? What's the probability of expecting it, right? Because we are saying just I'm expecting a value. I'm expecting 3, right? 3/4. But what's the probability of expecting it? Yes. And diminishes is a tricky word to put it because every time you roll, you have a chance of getting a 4, which is 30%. The question is how those probabilities are going to get stacked against each other. When we were talking about stacking probabilities, we had that problem before. Last class. Remember when we were trying to place objects around,
Yeah, 3 different objects.
right? In this case, we don't have to. We are not stacking 10 different objects. We want to stack 8 out of 10. Because we don't care what the other ones are. As long as they are not what we wanted, we are stacking objects. Right? So when we're looking at the probability, we are, right? Because we don't care. We don't care where the 4s are placed, do we? As long as there's 8 of them, maybe you got lucky. The first 8 was 4s. Or maybe you got unlucky. The first 2 were 1 and 2, and you're starting to sweat because then you have to roll 8 4s in a row, right? We don't care. So we're looking at combinations versus permutations. Yes? Right. So if I was going to write this out, what it would look like? Well, that's n factorial divided by n minus x factorial times x factorial. Right? NCR. Yes? Same formula. Yes? Yes. Okay. Right. We need to roll 8 4s. If I flip a coin once, what's the probability of getting a head? 50%. If I want to flip a coin twice and get 2 heads, what's the probability? It's 1/2 times 1/2, right? So in our case, we are talking about probability of success. How many times? X number of times. Right? This means P times P times P times P times P X number of times. Is that it? No? Yes. So we need to multiply this times fail. How much of the fail is there? However, trials were we don't use for successes.
Is it 2 or 7?
In our case, Q is 0.7, but the top would be 10 minus 8, so it would be 2. Right? So our formula is exactly that. And that's P of x. All right. Let's look at the numeric part. Numeric part says, hey, P of 8 equals to 10C8. Yes? We want to get 8 arranged out of 10, and there are different places. But for that to happen, we need to roll 8 successes. So that's 0.3 to 8th power. Right? Because we need to roll this. I'm not asking you for probability. We can have a couple 4s and then break a couple 4s. Or we can have all the 4s at the beginning or all 4s at the end. There need to be 8 places need to be occupied by 4s. which means we had to roll 8 fours, right? And that also means we need to fail twice. 10 minus 8. We're going to fail twice. So this is 10C8, 0.3 to 8th power, 0.7 to 2nd power. Okay, let's take a look at it. What's 10C8? How big is that? You have a calculator. This is done by the calculator, right? 10C8 you can do on a calculator. You don't need to do this. You plug this into a calculator. And that comes out to be 45. It's 45 ways you can arrange 8 objects out of 10 if you don't care about the order. Times this. Now this is 6.561 times 10 times 10 to negative fifth. And I'm putting a lot of decimal places here because if you start rounding, you're going to start losing things. And then you multiply this times 0.7 squared, so 0.49. The big dots are just for multiplication, so it's easier to see. So probability of 8 comes out to be 0.
Is that a comma or is that a?
This?
No. The 6.561, is that point?
Yeah, sorry.
Oh, that was 1,000.
Yeah, no. That's why I like giving commas and points, because then they won't mix with the multiplication. But I don't mark my thousands on the bottom. I mark them on the top, if anything. And this is, how big is this?
It's 0.1446%.
How would you plug that into the calculator? The 10C8?
Yeah.
10C8?
Yeah, how did you do that?
45.
Okay,
I have the same calculator as you.
you have a calculator?
I have
10, probability, NCR, 8.
Okay, thank you.
Mm-hmm.
I can ask you.
Where's the power?
10, probability, where's this one?
Oh my God.
Enter, right?
Okay.
8.
Oh, okay. Thank you.
Everybody,
Probability 8? Oh, yeah, there it is.
yep, enter. You have NCR. Oh, here's. Let's go 10, second NCR, 8. And that gives you the 45. Cool. Yep, that's the one. Anybody else? You got it too? Cool. All right. Cool. Again, this is great, but you can plug this very easily out. So what usually you will see is this. Now let's see how much time we have. 3:21. Okay. All right. Let's. What do you want to do? All right. Let's do another example. Let's say I'm gonna still stay by the loaded die, So, example 2. Let's say I'm going to talk about the loaded die. So, loaded die had n equals to 10, p equals to 0.3, q equal to 0.7. That was the loaded die. 4 at 30%. Right, that was the loaded die. So we still have the same loaded die from the previous example. What's the probability of rolling at most 8 fours? What does it mean at most?
Less than 8.
So give me specifics. So 8? But can we have 7? Can we have 6? 5? 4?
We need a table for this.
3? 2? Probability of 1. Is that it? You sure?
0.
Ah, yes, 0. Now, my dear, we have to do every single one of them this way. Shh. You're ruining. They're about to be miserable. Oh yeah, but you still have to plug it in for 9 times. But.
You can add that, right? Oh, yeah.
Somebody with no life
And a computer.
produces, and a computer, produced a table. Does everybody have this handout with the tables? Because I have some extra ones, so I was giving them out when probably some people of you weren't here. You have one? That's okay. I got you covered.
Thank you.
It has some charts, some tables in it. That's all the tables you're going to need for this class. All right, so if you look at it in the back, is everybody?
I have one normally. I just did it for you. Thank you.
I'm not judging you. There is no judgment in my eyes. Right, if we flip to the last two pieces of paper, you look at the very top of the table. It says binomial probability distribution, and then it says what? C and R, P to R, and Q to NR. So just in case you forget this formula, there's a cheat sheet on your table. Illegal. But what can you do? I stole the table from somebody else. I'm not going to make my own table. Right, so you have the formula for on the top, just in case you forget. So how do we read this table? This table has a couple things. First of all, it uses R instead of X. So there's just a little thing. So if you want to take a pencil and just say that this R is an X, that's fine, right? But I'm just telling you that this table uses an R. And again, half of the textbooks I've seen use R, half of them use X, and the third half uses something else. If that was even possible. This is how the table works. On the very left, you have N, and this tells you how many trials you're going to run total. Right? The next column, next to it, very much more dense, the R column, tells you how many successes you want to get. Right? So N is the number of trials, R is the number of successes in those N trials you want to get. Then, horizontally, on the very top, tells you a probability. And again, it goes from 1%, 5, 10, 15, 90, and 95. In our case, if I give you a problem that has a probability that is not on this table, right? And I'm asking you for exactly 8, that means I'm expecting this. But if I'm asking you, for example, probability of 67%, and I'm asking you more than 2, abstract question, right? Use the table and just pick one of them that is closer, right? I'm not going to make you do this more than once or twice for very specific reasons on an exam. Usually it's going to be once, give me a very specific number. Inside of the meaty part of the table, you have the probabilities. So let's look at our problem. Our problem says n equals 10. So we flip the page to n equals 10. Somewhere here. Everybody found it? Okay. We got n. We scroll down to number 8. And what's our probability? Our probability is 0.3. So let's find 0.3 on top and 8 here. And what do we get? 8, right? Out of 10 and 0.3. And what do we get? 0, 0, 1. How much did we get? 0, 0, 1, 4, right? Our calculation is much more precise than the table. The table only goes 3 decimal places, right? So just mind you that there is a limitation. This is here to remind you that there's limitations. But, if we get stuck with something like this, do you really care about the limitations? The assumption would be that you would overestimate and underestimate things according to the table, right? They would round up and round down. So we're going to squint our eyes and assume that if we calculate on the table, we're going to get it about right. So how do you do it? Well, probability of 8, we already have 0, 0, 1. Probability of 7, 0, 0, 9. Probability of 6, 0.037. And we add those. And we just add those numbers together. So let's add those numbers together. So what do we have? This is 0, 0, 0, 1, 0, 0, 0, 9, 0, 0, 0, 9, 0.037, 0.103, 0.200, 0.267, 0.233, 0.121, and 0.028. And this is how you do it. Just add those numbers together and you're good. It takes some computation, but it saves you from this.
0.999.
Okay. Now, couple comments about this table, and those are important. Comment number 1. The values in this table are rounded. That's one, which means that single values are not to be considered very precise, as precise as you can see. Comment number 2, sum of all those values not necessarily will be equal to 1, because, again, we rounded. They're rounded, right? And comment number 3, which is the important one, that 0, 0, 0 that you see, 10 out of 10 at 30%, 0, 0, 0, doesn't mean 0. That number doesn't mean 0. There's always a probability of rolling 10 fours out of 10 at 30% per 4. It's not 0. So if you ever have to add things together and they get close to 1, you say about 1 or 9.999 or something. You indicate, you never write 1 unless I tell you to say what's the probability of rolling between 0 and 10 fours on 10 rolls. Unless I ask you for the whole thing, you will never get 1, even if the numbers add to 1.
In this case, it wouldn't be 1, it would be 99.9.
In this case, if you add all of those, it will be 0.999, I think, right? Or 998 or something. Okay? But in some of those cases, there's couple, they will add up to 1. They will, right? Conversely, you could always approach it differently. You could say, hey, I really don't want to add 8 to 7 to 6 to 5. I want to go 1 minus probability of 10 plus probability of 9. Would that work? It would. Right? Instead of looking for all of those successes, I'm just going to look at where it failed and go 1 minus all the failures. Right? I can approach it both ways, right? Because it's a binomial distribution, so it's either one or the other. So I could approach it this way, right?
So if you exclude Q, then it would be P. The remaining would be P.
Yeah. Right? So I could go this way, but if you go this way, this is 0, 0, 0, and this is 0, 0, 0. Right? According to the table.
Would you take that as an answer?
No. What I would get for an answer is but not 1. Close to 1, but not 1. Or 0.9999 or something. Any indication that you understand that those zeros, 0.000 on the table, doesn't mean 0. Regardless of how small the probability is, the chances are still there.